Alright, so in this video we're going to first start talking about the idea of center of mass, and then I'll give you a very simple equation to start calculating torque. So let's say that we had an object like a beam or something, and its mass is distributed, it's evenly distributed throughout this object. Well, the center of mass would be the point where we can assume all of the mass of the object to be. So point where we assume all mass of the object is. And that sounds kind of weird, right? Because how can all of the object mass be in one point? But let me kind of explain, giving an example where we have a board that's 20 kilograms, and then let's say I have just a tiny little dot that weighs 20 kilograms or has a mass of 20 kilograms. If I were to apply a force to this object that's 20 kilograms, we know that then that object would accelerate in this direction in line with the force, okay, by some magnitude. Right? If I have an object here, right, and the mass is sort of evenly distributed around, the center of mass is sort of like right in the center of the object. All right, this is my center of mass, where all the mass is, and it would behave very similar to this object. So if I were to apply the same force to this 20 kilogram beam at the center of mass, where I can assume all the mass is, then the object would behave exactly as if it was at a tiny point location, and it would accelerate upwards. So up until this point, we've been dealing with Newton's laws problems, and every time we applied a force, the object just moved in the direction of the force that we applied, right? And it accelerated in the direction of the force that we applied. So we have made the assumption that always when we are pushing or pulling on an object, that force is actually at the center of mass, right? Now we're going to look and think about, well, what happens if I apply a force that's not at the center of mass? So let's just draw a beam, another beam here, right, the same one. And if I were to, say, apply a force here, let's think about intuitively what is going to happen. Well, if I applied the force over here, my object is not going to go straight up, right? If I applied it at the center of mass, right, which is kind of difficult to do at this point because there's some friction, but if I applied it at the center of mass, the pen should accelerate upwards, right? However, if I apply the force on the end, you can see that the object wants to rotate, and it actually rotates about its center of mass. Let's say I applied a force over here, we can see that the object rotates. All right, so that's essentially what this entire unit is going to be about. It's going to be looking at forces and how they relate to rotation rather than just accelerating objects through space. All right. So we're going to begin by doing that by just doing some very simple torque calculations, and then we'll get into some more advanced torque in the next video. So torque is written with the Greek letter tau, and it's equal to the force perpendicular to the distance or to the displacement from the point of rotation, from the point of rotation. All right, and for these first problems, we're just going to assume that most of the boards and things that we're dealing with are massless. We'll come back and deal with things that have mass and use our center of mass concepts when we do more complicated problems. But it's easier to look at torque from the beginning by just assuming that there's no mass in the object and just sort of getting an idea of how force and distance relate to the idea of torque. Now, if you notice, force times distance, we've seen that equation before. Force times distance is work, but remember that that was force parallel to distance. So these are very different ideas, and this actually is not work. The unit for torque is newtons times meters, okay? But it does not equal a joule, right? And it does not equal work. So let's look at just some really, really simple calculations, right? So let's say I have a door and there's a hinge here, right? So this is fixed position, or this would be the point of rotation, because if I were to push on that object, it would rotate about this point. Right? So if I wanted to figure out the torque, let's say I were to push with 10 newtons at the end of the door, and let's say the door is just 1 meter this way, then the amount of torque that the door would be experiencing here at 1 meter would be 10 newtons times meters. Right? Now, let's say from the center of the board, I have, would only be a half a meter. And let's say I wanted to exert the same amount of torque to rotate the door about the axis. It's going to require more force, right? If you're closer in, it's going to require more force to get that to swing around. So if I wanted to create 10 Newton meters of torque at half a meter, I'd actually have to exert a force of 20 newtons at that location. But I would get the same amount of torque, which is 10 newtons times meters. Right? Now, notice that these are always, I'm showing that these are all perpendicular. So you may be given an example where, say, you're pushing at an angle, right? So if you were to push at an angle of the door, like that, then we would just have to find this component, based on whatever angle it is, and then use that in my torque equation. Right? So let's just look at one other example of, say, an equilibrium idea. Right? So let's say I have a seesaw, right? And there's some point here that's fixed. So this would be my point of rotation. And let's assume that the seesaw is weightless, or that on either side we have the same amount of mass, because this would be at the center of mass. All right, and that will make a little bit more sense later. So if I put a kid over here on this side, and let's say the beam is, I don't know, like 3 meters, right? So the total length of the beam is 3 meters. If I were to put, say, a 30-kilogram kid over here on the very end of the board, right? So he's pushing down on the board this direction, the whole beam would go like this. Then let's say his 20-kilogram brother, right, wants to sit on the other side. Where would he have to sit such that he would balance out his brother over here? So all of the force or the torque that's making it want to rotate this way would have to be equal to all the torque making it want to rotate this way, and so that my beam would balance. Right? So the torque on this side, the torque of this brother, would be his weight, which would be 300 newtons, times 1.5, because we said he's way at the end. So we have force times distance over here must be equal to force times distance over here. So we say 300 newtons times 1.5 meters must be equal to, over here, 200 newtons times x. And so let's figure out how far away that brother would have to be, or if you could even balance his brother. So he would have to be 2 meters away from the center of the board, which he couldn't be because the board is too short. So they cannot balance one another out in that position. Let's look at how we could move this brother. So let's say this brother's at the end, and let's see how we can move this brother such that they would balance. Right? So now over here we put the 20-kilogram kid on the very end of, remember, the board is 3 meters. Where would we put 30-kilogram kid over here such that he would balance? So I would get 200 times 1.5 newtons is equal to 300 times x. So 200 times 1.5, and then just divide by 300. Okay, so it would be 1 meter away. So we could put him at a location of 1 meter from the center, and then we would have the same amount of torque on either side of 300 newton, or 300 newton meters, and that would cause our beam to balance. All right, so this is really where we're going to start, is with these very simple force times distance, either calculating it with something about a hinge, like the door idea, or looking at um, uh, balancing something and making torques on either side the same.